Hi, my name is Alex Farrar, and I'm here today to present the first part of my PhD, which is on interpreting and validating translithospheric faults in the Central Andes, and to look into their spatial distribution and their control on the localization of the giant porphyry copper deposits that occur throughout the Central Andes. Thanks a lot to my co-authors, who are also my supervisors of my PhD. And thank you as well to First Quantum Minerals, who is sponsoring the project and has provided a lot of the data for the project. What is a translithospheric fault? Basically, a translithospheric fault is a long-lived zone of crustal weakness that penetrates the entire lithosphere, so the upper lower crust and the upper mantle. An example of a translithospheric fault would be a suture zone, where two terrains have docked together, and basically these sorts of fundamental weaknesses in the crust are recorded in the geologic record and are reactivated throughout geologic time. The intersections of two oblique translithospheric faults is a great place to localize permeability, as the diagram on the right shows. Basically, we think that intersections are providing a focus for both magmatism and also hydrothermal fluids from the upper mantle into the crust. There has been previous work done in the Central Andes on identifying regional scale lineaments and translithospheric faults dating back about 40 years now. Originally, the work started with the identification of a pre-existing architecture in northwestern Argentina, which also coincided with volcanic breakouts into the back arc in that part of Argentina. Geophysical data sets were captured about 20 years after that regional scale, and it was seen that these field observations were also highlighted in regional scale geophysical data sets. There was more recently, there was some work in central Chile and Domeco Basin relating large scale oblique structures to the localization of the supergiant porphyry deposits of El Teniente and Rio Blanco. So there's been work done in the Central Andes to identify adequate methods to interpret translithospheric faults. However, it's tended to focus on specific areas, so northwestern Argentina or an area in central Chile. However, there's been no study that covers the entire Central Andes to create a fully regional viewpoint of these regional scale structures, and to see if we can relate them to porphyry copper mineralisation on the scale of the Central Andes. The Central Andes contains 65 giant, so greater than 3 million tonnes of contained copper porphyry deposits, and it is the most important copper province in the planet. So thanks to First Quantum, we've got access to some regional scale data sets, really high quality ones as well. The image on the right is stitched lithology covering Peru, Bolivia, Chile and Argentina, and it's been made as seamless as possible across the borders so that we can start working with data on a regional scale. We've also worked with regional scale gravity across the entire region. This is ground station gravity on the left-hand side. That particular image has got a depth of investigation of about 30 kilometres into the crust. The middle image is magnetics, so that is the background image is satellite magnetics, which is obviously very coarse, but draped on top of that regional magnetic surveys, which actually cover most of the Central Andes. And then on the right, we have the location of recent volcanoes, so post-Miocene volcanoes, as the black stars, as well as hypercenter locations, so earthquake epicenters down to about 60 kilometres depth. So these are examples of data sets that we've been able to draw on to carry out our regional scale interpretations. Obviously, as well, we've been able to draw on previous literature that has been studied, and as well as we've looked into the tectonic accretion history or the construction of the western margin of South America, in this case since the Precambrian, basically looking at the different terrains that have docked onto South America in the last 700 million years, say. And so we've also marked out the suture zones of these terrains based on literature and our geophysical data sets. And what we've also done to interpret lineaments is we've done a lineament interpretation on each of our individual data sets, so the magnetics, the gravity, the volcanoes, as well as the lithology. And we've split the lithology based on the recognised 7 tectonic cycles that have affected the Central Andes since the Precambrian, and we've done a structural interpretation on each one of those tectonic cycles as well. We layer each interpretation on top of them all into a layer, and we basically look for overlaps between the different layers. And we're looking for repeating structures or repeating lineaments in the different totally independent data sets. And we produced a lineament map. However, that lineament map is simply a GIS workspace. It may be real, may not be. So the next step was to validate our lineament map in the field. What does a 500 kilometre long gravity and magnetic lineament that you might also see in geology look like when you stand on top of it in the field? So we've gone and done that. So we had about a year and a half's worth of field work. Unfortunately, it was this year as well, but COVID stopped that to work in this part of the Andes. And so southern Peru, Chile, and western Argentina, we got out into the field and we stood on top of these two lineaments to see, to basically ground truth them or to erase the ones that we just simply see no field evidence for. So we started with 2 lineaments which are well recognised and accepted in the geologic community. The Domeco fault system, which I think everyone has probably nearly heard of that works in economic geology. So that was one that you see in all the regional data sets as well as the geology. It's also obviously also a prolific corridor for copper mineralisation. So what we see there is basically an elongation that's about 200 kilometres long. We see a zone that's hundreds of kilometres long and roughly maybe 30 kilometres wide of brittle structures. So some of these structures in the northern end of the corridor here, such as the West Fisher Fault, have offsets of up to 30 kilometres that have been interpreted. But most of the structures are actually just small scale brittle structures by themselves, not particularly important, but they're essentially the surface expression of an upper propagating translithospheric fault through younger layers. And of course, we see this same orientation of lineation in our lineaments from our geophysical data sets, and et cetera and so forth. This is gravity in the background here, and you can see there's a very important gravity break that coincides with a series of really important mineral deposits. This is the Antofagasta-Calama lineament, which is an arc-oblique northeast trending lineament. We see the same thing here. We see seemingly unimportant on a single scale series of brittle faults that is consistent, traceable for 200 to 300 kilometres across the Andes. We see active faults right now emanating through the cover sequences. This is a throw of an active fault through gravel that's pretty much a linear vector line for 30 kilometres. And we see volcanoes on the eastern side and the volcanic arc aligning with this same trend. So basically, this is a very, very quick summary, but we've done that for a lot of faults, and we've also combined it with literature and mapping done by the geologic surveys, and it turns out that we see a network of faulting, which tends to have a frequent spacing of about 80 kilometres. That spacing is probably due to the thickness of the lithosphere. It's a self-organising system, and at the intersections of those, a lot of the translithospheric faults, we see the really important porphyry copper camps. And that's all I'm going to talk about today. Thank you.